My name is Boguslaw Cyganek. I came from Kraków in Poland, not far from here. I work at the AGH University of Kraków. So my normal work is doing some research. I'm a scientist. I have a group of PhD students. So we are doing in computer vision, in AI, ML AI, edge computing, things like this. But also, for my whole life, I was programming in C++ mostly, but also in assemblies, other languages as well. And I teach C++, so maybe some of you remember my talk from the last year about teaching C++. So today, I will talk about pipeline architectures in C++. So actually, we'll have two parts. First is how we can make a pipeline in our code. And so this is the outline of what we'll be talking about. So we'll touch upon functional programming, but not too much, so don't worry. And it won't be about ranges library. So we will start with this a little bit, but we'll do something original out of ranges library, although it is based on the ideas. And also, the second part, I would say, is to present this new object in our toolbox, which is called std_expected. I don't know how many of you are already aware of using this std_expected. Oh, that's pretty much. Okay, so I will show also how to connect std_expected also in a pipeline, which is inherent to this, and this is called monadic operations. And also there will be a short end with a parallel version of pipelines, because this is also very. So these are the two key subjects I would like to focus upon today. Okay, so let's start with some definitions. So what is a pipeline? Well, I found this image in industry. We all know what is a pipe in our house. Sometimes it is stuck, so we know what is pipe and pipeline. But also we have Wikipedia, fortunately, so we can go to some definitions, and we see that a pipeline is in software engineering is a chain of processing elements such as threads, coroutines, functions. So mostly we'll see functions here, but we'll see threads as well. Arranged so that the output of each element is the input to the other one. Well, it's analogous to physical pipeline. Sometimes there is some buffering. There are also information that flows is often a stream, record bytes, we'll see that. And the elements sometimes are called filters. And they call this also filter design patterns, so we'll be touching upon design patterns today as well. And connecting elements is certainly a domain of functional programming. So, yeah, and there are some other issues with the definition of pipeline, but we will see many practical things. So what is the software pipe? Well, we know this from Linux. How many of you are using Linux as a primary platform? Well, majority. I'm mostly from Windows, and you will see examples made by me with Microsoft Visual Studio, because std_expected is C++23. So not all compilers implemented std_expected yet. But well, pipelines are really well known in Unix, Linux environment. So they were invented with the colleagues, but mostly attributed to Douglas McIlroy, 70s. And the pipeline is just a way for interprocess communication with message passing. So, yeah, we can connect them predecessor and to successor, and we have this famous operator vertical bar. So we can in our shell, we can write such a thing quite easily. You all know what it does, so I will go. So maybe you don't know, but maybe you know this anecdote about this interesting story happened in the 80s. So the famous professor Donald Knuth, was asked by editor of Programming Pearls, John Bentley, to write his version of implementation of a program for counting frequency of words occurring in any text. So he took this challenge, it was 80s, also because he wanted to show this literate programming approach. And he did. Actually, it is, I don't know if you are aware of such a kind of mixture of language. This is a mixture of comments and code. And now we have this with ChatGPT Copilot. We write one comment and the code is showing up. But it was something like almost 40 years ago. So he is famous because of this set of we call this seminal books, textbooks. Everybody was at least seeing this, of learning from that. But interesting response came from Doug McIlroy, who just proposed, instead of couple of pages of code of the Professor Knuth, he just proposed 6 lines of functional programming. So this is mostly translating all non-alphabetic characters to new line, then all capital letters to small letters, then sorting, then finding unique values, then sorting in reverse, and then printing a couple of best results. So that showed the power of functional programming. Certainly this McIlroy approach was slower, but not always we are at the just making the fastest possible computation. Sometimes there is a trade-off. So we know we have, as a warm-up, we have this ranges library. I started to program with ranges library and I like it. But they have some quirks and you get accustomed with them. So you can write like this. So this is normal function composition and have some results. But knowing that we can use this pipe operator, we can go a little bit more functional, like here. So we can use this as alternative. So we'll see that this composition in a pipeline with a pipe operator is just equivalent to composition of functions. So yeah, so how I came to this subject, because this is important, and these are some reference things. I read this book by Ivan, maybe he's somewhere around, and because I was just, as I mentioned, I teach students, so I was just gathering some materials to explain how ranges operate. So I was looking for some lectures explaining how this lazy evaluation works, and etc. And I came across this talk by Ankur Sato, Functional Composable Operations. So I started from his findings, and I proposed my extensions with the stud expected. So what you will see now is just follow-up of his idea. So his idea was like this. So this is just a startup for you to understand what we are doing. So this is the simplest implementation of this pipe operator. We just take a string, a function, and return a string. So we can define this like this, and we have such a pipeline without any problems. Okay? So yeah, we simply call, and we just choose this moved operation here, so we can take advantage of this possibility, and that's it. So just an example, writing a couple of functions like this. Yeah, we can compose, and here you have this nice composition. Yeah, but the thing is, well, this is just a basic example, so you will find the entire code on a GitHub. I will give you the link at the end of the talk, so don't worry. But yeah, so But this is too simplistic. We don't deal with strings. Certainly you can encode almost everything in a string, but that's not the way we operate in, let's say, modern C++. So the thing is, what if we wish different interfaces? So we wish something like this. So we have S, then F, then T, and T will be common output input to F1 and F2, but then we can have another thing. So such a simple thing will not work for us. So Ankur Sunkar just came with this idea, and I followed this. So he proposed, and that's what I found in his talk. So and he explicitly added this concept, not to intervene. If we allow any type T, then it can be ambiguous for a compiler when it sees such an overloaded pipe operator in our code and ranges code with pipe operator. So he put this required that this is not ranges T. And so that's the first thing. And the function parameter can be invoked with any type T now. And also we have this constexp. So if something can be computed with constexp values, it will be computed during compilation. And we call this std_invoke. And we have this std_invoke result helper to deduce the type. So this is the type returned by the function f with an argument t. Yeah? So for now, you see that we are talking about functions with one argument, but we can fix this later by the mechanisms of functional programming. And also we use this std_invoke, which is quite useful here, because it allows us to deal with any callable, not only a function, but it can be a function pointer, function object, member function, etc. So that's the story. And he came with another problem. What to do if we have a problem in the chain? So there is an error in the chain when we are processing. How to deal with that? Certainly you can throw. But this is like a tender. You can just blow up everything, and you must be sure to catch this error. So it's possible, but this is heavy-duty operation. So he came with this idea of using optional, and I worked it out further just to use std_expected. So what I'm building from this point on is just using std_expected. So for you, I think std_expected will change the way we design the interfaces. So it is, I would say, better version of std_optional. So if you are using std_optional, consider using std_expected because it gives you more functions, more opportunities. Although the two are very, very similar. From std_expected, you can make std_optional quite easy. So that's the main idea. So now, on the green screen, we jumped, like in HTML, we push the link, and we are in the domain of explaining what is std_expected. We will return soon to pipelines, but now we have std_expected. Certainly you can read. I encourage you to read, but we will not read it now. I just made, from a CPP reference, I just made a short overview what you can expect from std_expected. So exactly, this is the object which contains one of the objects, a value or an error. So expected or unexpected. Neither but. It is either one, either or. So it can convey this notion of a normal object, normal flow, or some erroneous situation. And it is a wrapper type that contains, let's say, expected of type T or error of type E. It is stored directly. There is no dynamic memory allocation, which is usually good. There is a special class, std_unexpected, is a template class, to represent an unexpected value e. It helps to distinguish what we wish. When we initialize to the expected, we wish to initialize with an object or with an error. So this is the way, the channel to say to the expected that we wish to put an error. T cannot be reference, function type, specialized unexpected. There are some limitations. And very important thing, before trying to access an object, please call has value or overloaded Boolean operator to see if such an object exists. Because otherwise, if you try to, in other situations, to the expected, if it holds an object, it behaves like a pointer. So you can dereference to expected and have a value. But if you fail, you have an error and do the reference, then you have UB, which is even worse than having thrown something. Or I don't know why, maybe for performance reasons, they left this implementation like with UB. So there are also monadic operations, which is separate thing. We'll come to this in a separate part of my talk. And it can be used instead of stud optional. So just briefly, you will find this on CPP reference, no problem, and you will see examples, but to be sure that I covered everything. So we have a constructor, you can construct with an object or with an error. You have this operator Boolean, has value. You can dereference in two ways, like pointers, and you can call the value if you are sure it is present, or you can ask for an error if you are sure there is no object in stud expected. There is a function value or what to return if there is no value, and we can compare. And there is a couple more. So we will see, especially a separate group will be this monadic operations. So let's make simple example. Sometimes people say that an image is better than 1,000 words. So probably an example is better than a couple of man pages. So let's do something with stud expected. So because I'm dealing with vectors on daily basis, so I took such an example. Well, if we wish to normalize vectors so they have a length of 1, we need to divide them by each component by their length. So we wish to write such a universal function for this. So we would like to have, we can expect some errors because we would like to have any possible container holding our vector. Not only vector, but also stud array, also the list, whatever can be put here. And so we have this template parameter, and we have this stud expected here. So it expects like an object. This is our container with the type T. Usually type T will be some floating point type. And we have this one of these three possibilities expressed by this enum class enorm error. So we have such a thing. So we normalize, we return this stud expected. And we also have this concept here that we allow only operations on floating point data. So first thing, if we are processing, we have to get accustomed with that. We need to check for possible errors, as always. So first thing I'm checking if I have any elements. If not, I'm returning, look at this. It is sufficient to return stud unexpected, because it can be converted automatically to norm expected, because it is because I provide the error from the proper type. Then, if I have something, I can compute the denominator, but I am not sure if the values are not 0. So I'm checking, but certainly in floating point we cannot compare equals to 0. We need to check for some threshold value. And also we need to check if we are not coming with some infinite number or not a number. So if you are interested in this, I gave this talk 2 years ago on floating point. There are many good talks YouTube, so you can find some. And well, especially I would like to point out that we have so many good functions already in standard library to check for all these situations. And then we transform, so we divide, so we follow this formula, and we return V. So here we can make some experiments, but you can, well, I started with vector, but it works with std_array, std_list, and many containers. And here I generated empty zeros, and I wanted to generate infinity. Fortunately or not, I had to cheat a little bit on the compiler because it doesn't allow me to divide by 0, but I think I'm a little bit made it work as I wish. So continued. Okay, we call this normalize on each of vectors. And then we need to check if we have a value. So if we have a value, then everything is probably okay. So we can print the results. But otherwise, we have an error. So we can just print something. So if we go here to some results, here are the results. So thanks to std_expected, I avoided throwing, and I can deal with many possible errors. So the only one way on a programmer is just to make use case what possible errors can be in your function, in your path. So here are we'll return to this example. So now we are returning to the pipeline architecture. So let's take this idea, okay? I promised you to use std_expected instead of optional or other throwing or something, and let's draw this function. So we'll build our framework, our pipeline, on a set of functions. If these are pure functions, I mean not changing not having side effects, not changing something unexpectedly, then we can concentrate on each function at a time. Then we can connect them with this pipe operator. So we assume only we have the same types here. So everything in my proposition is based on input expected, std_expected, and output is std_expected. So this must be compatible types. So either the same or we can convert from one to the other. But we have no constraints on the other parts. So we can have like this and like this. Okay, so let's make some code. So again, we have concept operator, pipe operator. It accepts std_expected and the callable, and the results of this callable with std_expected will be the output of this operator, but we expect it will be std_expected as well. So we call this invoke, but all the time we are doing in the domain of std_expected. So everything will be wrapped in std_expected. And here we require that the function is indeed callable with std_expected, and that the result of this function is also std_expected. So I have so many std_expected, five of them here. But the result can be another std_expected. I mean, it is still std_expected, but different template parameters. That's the good point here. We have also the overloaded operator, because this one is accepting this forwarding universal reference, and we can have a const reference here for overloading, no problem. So let's make some use of this. But before we go to this, I will show you is expected, because I made this concept. I couldn't find it in the standard library. So I expect that the type T, which is now std_expected, has these two possibilities, these two subtypes, value type and the error type. So they are present in this type. And also, we require that there is a conversion to bool. So it is constructible from bool. So this works for me. But the thing is that we can we can check if there is an object, and we have that the referencing is working for us, and the last requires is that we have this unexpected. So what is characteristic here, it was already mentioned by other presenters during this year meeting, is just, it is interesting to observe this requires construction in this concept. So it forces the compiler to check if indeed this condition is true. Otherwise, without this second requires, the compiler will be happy with syntax. If the syntax is fine, then it is happy. But it's not checking if indeed this value evaluates to true. If you put another requires like here, it will. So returning to the pipeline architecture. Let's work out, let's say, simple but realistic problem. We wish to find similar images or similar texts. So what we are doing with my students and cooperators, we are looking for some, let's say, kind of hash codes, which we call embedding vectors. So these are used in large language models. For example, with such a model, Word2Vec, invited 2017. Or we convert images to semantic representation with visual transformers of deep neural networks. For example, we managed to find features which are something like 100 bytes to represent quite big images, and they allow very accurate content-based image retrieval. So that's the issue of our research. If you are interested, you can Google my publications or something, you can write to me. So once we have such representations, we need to compare them somehow. So again, vectors, and the common comparison measure is certainly the most common is Euclidean distance, but the second is this cosine, quite known. So this is just a product of normalized vectors. We already know how to normalize vectors, so we can build upon this example. So how it works? If we have a representation of opposite images, or semantically opposite concepts, so the measure will be something close to -1. So this is like fire and water. Then, from the other hand, if we have similar concepts like Coke and Pepsi, just a joke. So for me, they are similar, but maybe I don't have good taste. And we have something into these two, so we can have Coke and water. So, okay, so this is what, certainly if you go into details, this is more deep, and all these embeddings require some huge models, etc. But, well, mostly somewhere at the end, such a comparison is taking place. So what we are doing, we have a database with vectors. We need to load all these vectors, normalize them, compute distances, and find the best distance in our matrix. So you see, we have a pipeline. And in many situations, daily situations, we have things like this. So the first thing, we recognize we have a pipeline. Second thing, we recognize what possible errors can jump out at each stage. And then we design step by step, so divide and conquer. So this is what we are doing here. So let's start from the first block. So we define this is our error, so we have to expect it with the path and this possible error. And we have another end of this, so we have loading error. So loading can have more options for errors, like wrong path, no data, wrong data, etc. So I define this load expected, which is path and load error. And we'll have characteristic parts of each function. So the function is taking expected and is returning expected. And is taking some parameters. But look here, we'll have two parameters. So we need to deal with, in these frameworks, with two parameters. We will see in a moment how. And it will be like a pattern in this framework that always we need to check if we deal with a good object or with an error. So you will see such a line always. It won't be in monadic operations. So you will see in a moment. So we are checking some errors, some simple code. I traverse the directory. If it contains the accepted extension, using this contains from stud library, then I push back. And then we return either the object, this red exp, or unexpected, no data. I tried to, but I failed. So this is our first function. So if we deal with pure function, the question is if this is a pure function, if it is taking some right references and doing some move operations. So probably not. But if we try to think of designing in pure functions, then we are on the safe side. Another function, again, we already saw this definition of stud expected. We return another expected, which is vector of vectors already loaded. Again, I check if there is an object. If there is, I can traverse, I can open each file. Then I can read with this make move iterator, and we return, let's say, vector. It is not a matrix, maybe we can say matrix, but it's a vector of vectors. And normalize, we already saw this, so we can use that function, but we build the framework here. Again, we check if we have an object, we traverse all vectors, we normalize them, and if this is okay, then we write them back. But if not, then we return immediately an error. So we cannot compare vectors, for example, with not a number values in floating point representation. And compute distances, again, the same framework, expected an input, expected an output, checking for errors, then traversing a matrix. Now it will be triangular matrix because we need to compare, it is symmetric, so we need to compute only upper triangular, for example, here. And yeah, we can use inner product because we already have normalized vectors. So we normalize ahead, then we can do whatever measurement without repeating normalizations. And again, we return distances. And final thing, we need to find the best match. So it will be, for example, I put a query to the database, and it found me the most, the best fit of images, for example, or a text or whatever. So for this, we need a tuple with some x, y position in this matrix and the best distance, and we have again expected with this index value and possible errors. So again, we are going through this matrix and looking for the best value. We start from the lowest possible, asking numeric limits, which is quite useful in this context. And if we found it, we return this. If not, for some reasons, then we can return expected error. And now the most interesting part. Yeah, we can build our pipeline, finally, with pipe operators. So what we do here is we are just using this function carrying. So I mentioned that we have function with more than one parameter, and one is allowable in this framework, but we can fix the second or the next parameters with the technique called function currying. It is named after Haskell Brooks Curry, American mathematician who was just building some ground for functional programming. You can look it up, what he did on Wikipedia, for example. Then we can add quite easily to our framework, like this. And we haven't seen that function. We can, okay, now we have some results. I'm not sure I have good result found or some error. So first I will check if there is some value. I need to go to the second screen because it doesn't fit. So that's it. And if it has, and I can write, I found it, the position is this and this, so this is your dog, this is the dog most similar to your dog, and there is the output. Otherwise, I can deal with errors. But we have some problems with these errors, so I will return to this in a moment. So here are some simplistic examples just to fit on the slides. So we can have an output like this. So for a couple of files with vectors, we found it. And also you can use type ID to write what is the outcome of such a long call of expected, because sometimes you can turn off a part of a chain, then you will have, probably you can have a different output. So this is what I'm using for some checking in runtime. And also, if I put some errors, ABC are not values, so I have wrong data. But the thing is to know at what point, so we return to this. So again, go back to another option of pipelines. So you saw the custom overloaded pipe operator, but we can use monadic operations without redefining anything ourselves. So because toExpected is endowed with 4 monadic functions. So what are these functions? And then transform or else transform error. Don't worry, don't read this. You will see images in a moment, so I will explain what they do. So and then and transform are monadic, which accept a function which is called if there is an object. On the other hand, or else and transform error are endowed with a function written by us, which is called only if there is an error. But there are subtle but differences in interfaces. So let's see first an example. You will see in a moment what are the differences between them. Again, the same simple normalization, vector normalization example, but now, yeah, you remember we had these results, but now we wish to process because it returns expected, so we can apply or else, because we know that or else will be called with our function only if there is an error. So first thing, we don't need to check again if we have an error or not. So we are just processing errors, like printing something. But also, we need to return to the expected. So that's subtle. But we can have a success. So let's employ transform. Now we don't need to check if there is a success, because otherwise we would not be called in the transform. So we can quite easily output and return the value. Look at this. We are not returning expected from transform. That's the tricky part. Okay, yeah. So we have nice drawings. It took me many hours to make them, so please appreciate. But I'm sorry for errors. But images are better to understand. So if we have and then, you have two paths. Error goes like an error. But if there is an object, so has value is true, then my function f is called. So my function is accepting not expected, but the type t, because we are sure we have the type t, but I must return expected. But it can change the type from t to u. On the other hand, also for processing good objects, let's say, proper objects, not errors, I have transform. The same input, but the output is just an object, not expected. And that object will be, by the framework of monadic operations, wrapped into expected. So the output of these two boxes is the same, but the boxes expect me to define different functions. And I have another part to process errors. So if there is an object, it passes by, but if it is an error, it is passed to or else. You already saw or else. And I can return expected, but this time I have an option to change the type of an error. You see, I had E, now I have G at the end. And I have transform error, which behaves the same like transform, but for error types. I have E, I return G, but again, it is by the framework of monadic operations wrapped into the output expected T and G. So what the conclusion of this is? We provide the functions, and we have an option always to change something on the way, but not bot. So I can change either the object U, or I can change error if I'm processing error type, not bot at the same time. In the pipeline with operator, I just designed whatever we wish, but there is a price. Okay. So I have already said what is written here. So, okay, we can jump further on. So the images, you will have them. So that's the main point. So returning to the pipeline architecture, this time with monadic operations. So that's fine, but we have two problems. The first is, this is what I mentioned. I cannot change everything. I'm just stuck with some objects on the way. So I need to adjust my design. It is not that I take the previous functions like they are. So I don't have this flexible operation. I have this a little bit more constrained, but it is already written in the stood expected. So I don't need to write anything else. So that's good. And the second thing, which I was thinking for weeks how to solve, and probably many of you, how to deal with many errors in the pipeline. Because each function is bringing new errors, so it's supposed to inherit errors from the other in the pipeline, but I can change the pipeline, so how to inherit the functions? And by the way, we cannot inherit from enum class. I don't know. Is it good or bad? But so what I devised here, couple of solutions for this. Look at this. So we have different errors. We check if we have an object. So we return an error if there is an error. But I cannot just pass an error, because there are two different expected types. So I need to translate the error. So that's the solution. I need to redesign my functions a little bit. Second thing with these errors, so what to do? I propose to use variant. So you will see it works fine. So, well, maybe you have better ideas. So that's the topic for the talk on meeting C++, how to deal with errors. So for me, variant worked. So you will see, okay, so now we have common errors in the entire pipeline. And I can quite easily add new. So I can, at any point, I can choose, okay, this is my error at this point, and I set concrete value of that error. So let's go to redesign. I already have this function, so what I need to change, I don't have expected on the input. You recall from the drawings. I have just an object, because the framework already checked if I have an error and then called me. But I'm returning expected. So I don't need to check if there is an error. I'm sure if I'm called, someone else checked that for me. So now we can do our pipeline with and then, and this a little bit improved or changed functions. And we have and then to print the result, or else to deal with an error. But recall, now we have a variant. So we need to use such a design pattern, which is called visitors, a static visitor, let's say. And here, I think it might be interesting to see, I use this overloaded helper class just to introduce all these lambdas, and then I can visit based on whatever error I have. But I'm sure that if I'm in or else, that I am called with an error, but I need to return expected. So that's the thing. Okay, So what we have here, some results. Again, my debugging with runtime debugging. You see we have this variant for all these errors. And the last thing on this talk, parallel version. I was thinking, well, it would be nice to have some more performance in these pipelines. So, well, let's start again from this framework. Well, this is our serial version, just the first with expected. Now, I just redraw them to fit on this page, and let's do such a thing. And now we have such a framework. So what we are doing, our overloaded pipe operator is connecting our functions, dealing with any stood expected. We are flexible again, but each expected is connected to the synchronized queue. And operator is taking the function and such a queue and is creating the output queue for another function, and so on and so on. So here we can have one thread or a thread pool, whatever. We can have whatever queues. They must be synchronized, certainly. So I made a simple experiment. So now it is not just very, very simple. Sorry for that, but I needed to fit it. So this is a payload. So this is my object. I'm doing something with it. I can encounter a couple of errors when dealing with this object. And so what I am doing, I define stood expected. I have payload and possible object. So then we define what kind of functions can process my payload with this error. So like before, the function taking expected and returning the expected, except for this, that in this example we are taking the same expected because we don't have much time to deal, but you can rebuild this example quite easily. And I implemented very simple synchro queue. And again, look at this. Stood expected is giving us many opportunities when we return an object. Because what happens if I'm calling pop operation from the queue and the queue is not ready? I'm blocked as a thread. But I can return some message to the calling thread that, okay, the object is not available, you can do something else. Or in our framework, we have such a problem that we need to inform the pipeline that we process all elements already, so the threads will terminate. So we can pass such information in expected here. So I'm using queue, mutex, conditional variable. You can find the code on my GitHub. I am not citing this. And I'm using also shared pointer for these queues. But most interesting part is coming. So here is the new overloaded operator. And as you see, it accepts one queue, it accepts one function, and it creates another queue, output queue. So here we create the output queue. It is shared pointer. And then we call the thread with some thread function. And we provide this function with input queue, output queue, and our, let's say, cartridge function to do something. Yeah, so this is just the thread. And then we detach in this realization, and we output our queue. So now the thread starts working. It starts working, looking, is there anything on my queue? Nothing, nothing, nothing. Then finally, if it finds something, then it calls the function. So here is the function for each thread. So what it does, it pops element. If it is not available, do something, sleep, good opportunity. Then I need, at least in my framework, I needed to program somehow to stop this. So I put the stop token in the text, just quite easily to show the idea. If the stop token is detected, it can be done with stood expected again, then I'm done. I jump out of the thread function. Otherwise, I run this cartridge function, which is my external function to this framework, and I push on the output queue the result. And here are some functions, because this is general framework, so I must check at the beginning if B is available. Then to the text I'm adding 2, and to the value I'm adding 2 integer, another function just to show you how does it work. And here we have the most funny thing. We start something, we push on the couple of objects, the quick brown fox, and the stop token. And then we start our queue. So with this, we can have such a construction quite easily in a couple of lines. And if we are here, it means that the stop token was probably detected, so we can wait for the results, and we can print the results on the screen. So here are the results. So the quick brown fox, but at each step we added 2, 3 to the text. So all this, there were 3 functions, and so that's the main majority of what I prepared for you. I have a couple of slides with literature, because this is very fundamental problem in computer science: pipelines, pipes, functions, functional programming, threads. So I was looking what other people did, and this is very interesting, by Jonathan Bocara, C++ pipes. It is, I don't know if this library is finished or not, but it is quite interesting, and there are many interesting information you can read about pipes, especially that there are pool-based pipes like ranges library. So the next component is asking something, so we can have this lazy evaluation, but there are also these push-based components like ours, where some output shows up and is pushed to another elements of the chain. But in such a framework, there are some fork, some unzip operations possible. And look at this. Jonathan is using other operator, this overloaded right shift assignment. Why? Because this right shift assignment is right associative. The pipe operator, which is binary OR, is left associative. In C++, we cannot change the association rules of overloaded operators. So quite interesting idea. I don't know what is the current status of this project, but you can find this by Jonathan Bocara. Quite interesting. I also found such a parallel task. There is a scientific paper connected to that. The guys are building a graph of possible optimal connections of elements and then connecting them in a more sophisticated pipelines. Conclusions, finally conclusions. A pipeline architecture. Well, maybe I convinced you, maybe not, maybe you are already convinced, but can be efficient, very efficient in practical programming, especially, we can divide the problem in smaller chunks and develop each separately. We can ourselves implement this operator quite easily, as you saw. And stood expected is really useful and changing the way we program in modern C++, whatever modern means. Probably you can rethink your interfaces right now once you know stood expected is and will be available in future versions. You can use monadic operations. So if you need a pipeline, you don't have time to overload the pipe operator, you can always call monadic operations, but please keep in mind that there are some peculiarities. So for example, returning expected from transform will make your expected wrapped in another expected. So you'll have double expected at the end, etc. Yeah. And that's probably for another talk, multi-threading pipelines, but I put it here because I'm not sure if Jens will invite me again. So you have this in this talk as well. And there are other frameworks if you are interested. It is and many authors of libraries who use pipelines, they admit that it can help in testing, because especially if you stick to pure functions, then each function is just a box, self-contained box. You can make some tests and mostly be sure it operates as you expect, with expected. I think that's it. So here are the links to the code of the examples I show. There is my book about programming. Last year I had a talk about teaching C++. So in the book it is organized, we teach at my department, but there are many ways to do this. So I will be more than happy to discuss with you either pipelines or teaching scenarios, etc. So thank you very much.
Thank you for the presentation, and it's so interesting. When we are introducing the interface, it reminded me of the chain rule in calculus, and also the matrix multiplication between different dimensions of the matrix, which is a very common part of most of the machine learning tasks. And my question is, so how should we compare the performance of this comparing to the normal or general procedure from the compiler's perspective? Because in this implementation of these functions, you also have the branching, like error handling. Yeah. So I'm not sure, is it a big chunk after compiling, or like some other things that we can optimize, we can consider as a huge optimization? Yeah,
good question. Well, the simple answer is measure. So, but probably this is not what you expected from me to answer. Well, the good thing is it is divided into parts. So you can build like Lego bricks. You can put them together. So there is no obstacle of if you have huge chains, you can divide them into some components, compile them separately, even well, so you can arrange it. So this is the good thing. The bad thing is, as you mentioned, you have everything and you have to deal with all these errors. So this is why I'm using variant here. You can think of a variant of your types on the way as well. So for sure, this is not ultra optimal in performance, neither in compilation. I cannot say, but well, probably this is reasonable because there are no iterations or something. We are not doing meta programming or something. But like this comparison, McIlroy and versus Donald Knuth. Donald Knuth's solution was much faster, but not always we are interested in being ultra fast on something. We are interested in to be flexible, to have this good design, to have this reusability. You can reuse such component quite easily.
Got it, thank you. I think it makes sense a lot when doing, like, for example, implementing the training code for machine learning tasks. Sure. Because each epoch we have like this very clear, like natural language description of what we are doing, right? So yeah.
Actually, it is organized this way, but usually we program with Python. Sorry for that. Same. On this, I will escape.
Thank you.
Hi. What do you think about the dangers of operator overloading, especially an operator like OR, which has another meaning, especially templated, implicit conversions, all that?
Yeah, another very good question. So one of the solutions was proposed by Ankur. So he put this not ranges because he observed that interfered with ranges operator. And in my code, I didn't present this, but at the end, there is ranges library called, in all these examples to show that they don't interfere too much. But it can be in real life. My short answer is use namespaces. Closing the namespaces, make components.
But that means if I put the operator in a namespace, then I have to say namespace operator, which makes the code kind of ugly.
Well, it depends of what are you doing. If you are doing separate library components, you can have a namespace for entire your library. For me, it is fine. If you need to, I would say it this way. If you need a specially namespace to be created to use that, don't use that. So it's supposed to work. I use namespaces as well in the examples, but it should work in open namespace as well. So you can using namespace std, redefine your operator, and it should compile and work fine. Okay. With all these concepts, actually.
Thanks.
Hello. Thanks for the talk. Fantastic stuff. Some questions from our online audience.
Okay.
Marcus Verle asked, I may have missed a detail. In one of the later examples, you dropped the pipe operator for and then. What's the advantage of this?
Well, there are two different approaches. And then is on the board of stud expected. So with and then or else, you can do whatever you wish with any stud expected without overloaded pipe operator. But the good thing is you can mix them. You can have overloaded pipe operator. It is returning you stud expected, so at some other point you can use monadic operation if it fits you. That's flexible.
Sure, thanks. Another question from Daniel Gavirla. Which are the mappings between the monadic operations of the stud expected to the standard to monadic operations from Haskell, bind, and return?
I'm not sure I can compare to Haskell, actually. Anyway, such comparison is useless. We have them implemented this way. So the question is, my founding about this monadic operation is they are a little bit redundant. By this, I can say majority of actions I wanted to do, I could accomplish with and then and or else, without transform or transform error. But they are in the framework for some reason, so.
Sure, thank you. That's all.
Thanks.
So, thank you again for the very interesting talk. You talked about stud expected. It's really useful in that context of pipe, so we're doing something similar. And a colleague of mine also wrote an expected, I think 3 years ago or so, very early while it was still in development. So this stud expected seems to leave a lot of chance for unexpected behavior if you don't use it correctly.
Yeah, unfortunately.
Yeah. Is there a good reason to have it exactly that way? So
I am not sure. I don't know the implementers. I use the Microsoft compiler only. So this UB is scary. But it can be found by sanitizers, and it's quite easy to see that you are not checking for. And with monadic operations, you don't need to check because you are sure monadic is called always either with an object or with an error. But you're right, many companies implemented your own expected. I think in the Boost library there is also kind of.
it seems easy to make it safer. So
yeah. Probably the performance reasons. So it is like SQRT. You can call SQRT with minus value. No one checks that. Why? Because if you check in milliards of operations, then it would be overkill. Yeah. So this is up on the upper layers of software to check that, or make programming by contract, assert, static assert. It saved my way many times. Okay.
Thank you very much.
Thank you. Thank you.